Hello everyone. So in this presentation, let's discuss about the copy on write mechanism that is implemented in modern operating systems. So what exactly is copy on write? So copy on write is a memory optimization technique that primarily aims at resolving the overheads associated with allocating memory while creating new processes. So what copy on write basically does is whenever a new process is created, it just maps the page table entries of that particular process to already existing pages so that it does not require or does not make the operating system to create new processes and makes them available immediately. So only when any of these newly created process wants to make a modification to any of the pages it is mapped to, only then the operating system will make a copy of that particular page which requires a modification and then update it by making a copy of it. So while we talk about copy on write and paging, we'll just have a short recap on what virtual memory and virtual memory pages are. So virtualization is one of the core techniques that is available in present day operating systems. So with virtual memory, each process is given its own address space, which we all or which is commonly known as the process address space, which is a collection of pages. So depending upon the process's size, which is basically the code and data size, also the stack set of pages is allocated for each process whenever a new process is created, and each of these pages is mapped in a data structure called the page table, and it is stored in the page directory so that when the CPU moves from process A to process B, it loads the virtual pages of that particular process so that it could know the context of the process, which is like the instructions it needs to execute. So here we could see abstraction of memory virtualization. So on the leftmost side of the slide, we can see a column which represents the virtual memory, which is where each block is a page or virtual page which would belong to any of the available processes in the system. And conventionally, the most common memory page size is 4 kilobytes. So any process could contain n number of such pages depending upon its requirements. So each of these pages are mapped to the data structure as discussed earlier, which is called as the page table. So the page table would know where each of these virtual pages are mapped to. I mean, where to which process each of these virtual pages are mapped to. And then based on this information, it will then map that particular virtual page to the physical page. So let's say there is a process A, which consists of 5 such pages. Each of these pages will be loaded into the page table. So when the CPU is looking to execute process A, it will use the page table, locate virtual pages for process A, and then load it into the physical memory so that the CPU can access and execute process A. So moving on, here we could see an example of how copy on write is implemented. So initially there is process P, which consists of 3 pages, pages 1, 2, and 3. And when a new process Q is created, initially process Q is mapped to the same pages as process P. And now, as time passes, let's say process P needs to make a modification to one of its pages. So in that case, it will raise a modification request to the operating system. So the operating system will then handle it, create a copy of the page which requires modification, and maps it to process P. So once a copy is made, uh, process P can proceed and make some changes, which basically will be a write operation. So now process P will write those changes on a copy of the page, and thus we arrive at the name which is copy on write, right? So one of the most important system calls in the context of operating systems is the fork system call, with which the operating system aids the process of creating a new process from an already existing process, which are referred to by the names parent process and child process. So conventionally, when the fork system call is made, a new process or the child process will be created, and a set of pages will be allocated to it. And these pages usually contain the same context as that of the parent. But on the copy of write implementation, to reduce this additional overhead with allocating pages, whenever fork is called with the copy and write context, the child process is mapped to the same pages as that of the parent, so that both of these processes can use the same pages whenever they are executed. But in case when any of or either of this process wants to make a change by write operation, in that case, they would raise a modification request where the operating system will handle it and create a copy of the page that particular process needs. Here, let's say the child process needs to modify one of the pages that it is mapped to. So in that case, it will raise a modification request and the operating system will allocate a copy of that particular page and map it to the child process. So now the child process can proceed and write some changes to this new copy and then use that particular page whenever it is executed. So this modification request, which we talk about, is basically a page fault uh, handler, which is one of the memory management protocols that is available in the operating system. So here, when the child process needs to make a modification, then it would raise a modification request, which will be handled by the operating system as a page fault. So initially, when this request is accepted by the operating system, the new page that is needed by the child process will not be available. So the operating system will handle this page fault, allocate a new page for the child process, and copy the contents of the page to the newly allocated page. So here, the child process can then make the modifications which it is intended to be done, and then use the newly updated page for its operation going forward. So next, here we have a representation of page translation and fault handling. So that is represented here. So CPU uh, in the RISC architecture is, as we all know, is a load and store architecture. So these instructions are available in these pages again. So the CPU needs to load a page, access each 4-byte instruction from the page, and then execute it. So this is the same principle that is applied for data too. So every information that is needed by the CPU has to be loaded from the memory and then acted upon. Uh, these memory which we talk about here is again pages, and these instructions change from process to process. So we talk about the pages that is bound to each process. So collectively, it is known as the virtual address space of the process or the process address space, which again is a collection of pages. So in essence, the CPU has to load a page, access each 4 bytes from the page, and then proceed to either execute it or use the data. So this operation involves assistance from separate units such as the translation look aside buffer, the page table, the secondary storage, and the interrupt handler. So when the CPU looks for a particular virtual address inside a virtual page, it usually accesses it from the translation look aside buffer or the TLB. So if that particular address is available inside the TLB, then it will load it and proceed to execution. But if it is not available, it will raise a TLB signal. So the next level of search will happen in the page table, and the page table will contain the page entries of all the processes, or all the pages that were used by the processes more often. So if that is available in the page table, then it will be loaded into the TLB and the CPU will be using it. But if it is not available even in the page table, then a page fault will be raised, and that particular page will be logged in the secondary storage of the disk, and it will be loaded into the page table. A copy of it will also be loaded into TLB so that the CPU can access it and continue with its execution. So this is the overall process that is usually happening in memory management systems that use a paging setup. So here again we have the summary of page translation and fault handling. So the set of addresses are available inside the virtual memory. So the CPU can access each such entry from the page and use it for execution. All these entries are stored in the TLB, which contains the base address of all these pages. So the initial lookup will happen in the TLB, and if it is available in the TLB, then the page will be accessed directly. And if it is not, then the next level of search will happen in the page table or page directory. So if it is even not available in the page table, then a page fault will be raised, and the operating system will load that particular page from the disk and add it to the page table, and then it will be loaded into the TLB, and the CPU can continue with executing it. So, so again, for this process, we do need a set of hardware elements as used. So there is this memory management unit, which contains the transient local buffer, interrupt handlers to handle the page fault, and a few other things. So it's more of a protocol driven or event driven thing. So when a page fault is raised, that particular page will be located inside the secondary memory, loaded into the physical memory, which is the RAM. So a copy of it will also be stored into the TLB, which is a cache memory, which is quite close to the CPU. So the CPU can access that particular page and continue to execute it. So now we will see some of the advantages of the copy on write mechanism. So the first thing is faster process spawning. So what does that mean? Since all the newly created processes map to the same existing pages, or as we call as shared pages, whenever a new process is created, just the page table for that particular process is created and the entries are mapped to the already existing pages. So this eliminates the additional time that is needed with page creation, mapping, copy, and then adding the entries to the page table. By mapping or utilizing shared pages, we are also reducing the usage of memory that is needed, say, per process. So by mapping multiple processes to same set of pages, the amount of memory that is needed is significantly reduced. So in virtual environments, by making multiple process or multiple instances point to the shared memory or shared pages here, the response and operation is quite quicker than the conventional method of you know allocating and managing instances. And for disadvantages, there are quite a few. So the first thing is the copy overhead. So let's say after the initial allocation, and we have n processes in the system, and each process needs to make an modification. Then we need to make n number of copies of the pages that require modification and then make the necessary changes there. So this could be quite a costly operation, and it again invites copy overheads that is proportional to the number of pages that is requiring a modification. And since multiple pages are mapped to the same page or the shared pages, then it is quite complex to maintain or manage how these pages are mapped within each other, so that when a particular page is no longer needed, uh, and it can be reallocated, then it must be checked up until the last reference to ensure that that particular page is no longer needed by any of the processes before proceeding to deallocating it or freeing that particular page. Since multiple processes make or have access to these shared pages, in case of any mismanagement, then there could be some security and vulnerability issues where there could be some unmapping and uh, page table modifications that is not intended, so that it could corrupt the way a particular process is being handled. So in real or when we talk about real life scenarios, one of the other critical component in terms of managing disk memory is file system. So the QNX PowerSafe file system is one of the products from QNX, which uses copy and write based file system implementation. So usually when we talk about the memory management, so we have the super block, the inode bitmap, the data bitmap, and the inode blocks, and then the data blocks. So whenever a particular inode is initialized with a set of data blocks, then the super block needs to be modified. So based on this approach, this QNX file system maintains two superblocks, a stable superblock and a working superblock. So the stable superblock points to the most recent version of the file system, so which holds the necessary metadata such as the number of blocks pointed by each inode. And then whenever a change has been made, a change could be some write operation, addition of data blocks, or freeing of data blocks. Then these changes are stored in a separate superblock, which is called as the working superblock. And for every periodic interval, these superblocks are changed, meaning that whatever has been updated will be made as a stable superblock, and then when the next change is made, it will be stored in the working superblock. So for n cycles, this keeps changing, so that at the nth instant of time, the most recent version of the file system is available in the stable superblock. So this enables a quick generation of snapshots by since it is refreshed periodically, and whatever changes that are not needed are flushed, so that the next set of changes can be stored in and can be refreshed. And other such file systems that are used include the B3 file system, Zeta file system, which offer their own flavor of copy and write implementation. And talking about real world applications which use this copy and write mechanism, we have the Android Zygote, which allows multiple Android applications to share the same library pages, so that they offer faster operation and are quite responsive. With Dockers and containers, so each container will again map to the same shared region up until one container needs some modification. Then in that case, it will require a copy of the subset that requires modification and write its changes there. We have the virtual box, which offer different instances for each operating system. And whenever a change is required, then a request will be raised to the virtual instance manager, and then that particular request will be serviced. We have the B tree and CFS file systems again. And there is also Git, so which contains different versions of the tree, and it can be merged to the main branch only when required. And so now we can go to the final summary where we will recap what copy on write is and how beneficial it is. So as copy and write is based on sharing pages across processes, it primarily optimizes memory management by reducing overheads associated with allocating memory whenever a new process is created. There is on-demand page duplication. So one day when a particular process requires a modification, it will raise a modification request in the operating system. Will handle or treat it as a page fault, allocate a new copy of that page, and then map to the process so that the process can make its modification or write its modifications there. Since we eliminate the need for allocating pages whenever a new process is created in larger scale, it offers a lot of performance boost by reducing the time that is associated with process creation. And once memory allocation is eliminated, uh, we also talked about the associated hardware units that are dealt with in case of allocating memory. So by mapping already existing pages, the usage of these elements or entities is also reduced, significantly reducing the overhead that is contributed by these elements. So when we talk about the advantages, we also need to be aware of the decent trade-offs and the vulnerabilities that are associated with copy and write page. So before making any pages or before freeing any pages, it must be ensured that that particular page is no longer needed by any of the processes that is available in the system before freeing it, as without proper check, when a particular page is removed, it could corrupt the operation of that particular process and could crash the system. And now we have some of the references that were used for this particular presentation. I'd like to thank all of the contributors for offering me with the necessary information that was needed to do this presentation.